This video is about photoelectron spectroscopy, which is a method that provides some empirical evidence that supports the quantum model and gives insight into the fact that shells have subshells. Remember the photoelectric effect? Here we can see as the photoelectric effect is taking place in this simulation that even though the wavelength is short enough, the energy is high enough for these photons to produce the photoelectric effect, some of the electrons are moving faster than others. So this indicates that the electrons are being ejected with enough energy in some cases that there's sufficient kinetic energy for them to move very fast, but others have less kinetic energy as they are moving between the negative and the positive. Let's try and think about what might be happening as the photoelectric effect occurs. What you're really doing is you're taking an electron and you're removing it completely from the atom. So thinking about a simple model where the shells are just represented by not the quantum model, but just these kind of regions in space around the nucleus that are increasingly large in size. Imagine that you have this electron that's in shell 4, for example, and you're removing it from the atom. When you move from orbit to orbit, remember that the change in the electron's energy is minus b times 1 over n low squared minus 1 over n high squared. But what's n high? In this case, n high is actually infinity. So if you substitute for infinity for n2 high, you get something like this, that delta E is equal to minus b times 1 over n low squared, which would be like 4 in this case, minus 1 over infinity squared. But 1 over infinity, they say that it's undefined, but if you really think about it, if you have a number that's getting larger and larger and larger and approaching infinity in the denominator, that basically is 0. So that just takes this out, and it's just telling you that the energy it will take to remove this electron by photoelectric effect is a fixed quantity, and it's equal to, Bohr's constant divided by 1 over whatever shell it's in squared. That amount of energy that is required to do that is called the binding energy, or sometimes it's called the ionization energy, because you're making an ion with it is what you're doing. If the atom is bombarded with a photon that's too low energy to remove the electron, in other words, the energy of that photon is less than the binding energy, nothing's going to happen. You might cause a transition from shell to shell and get that line spectra thing going on, but you're not going to ionize this atom. You're not going to remove an electron from it. However, if you have a photon that has more energy than the binding energy, not only are you going to remove the electron from the atom, but after it gets removed, the extra energy is going to show up as kinetic energy, and the electron is going to be moving. So here's the situation. If we are bombarding this metal plate with a photon that has energy less than the ionization energy, no electron is ejected. If we have a photon energy that's exactly equal to the ionization energy, the electron is ejected, but not with any extra kinetic energy. If the energy of the photon is larger than the ionization energy, then the electron will be ejected, but it will also have some kinetic energy. It will be moving. And if the energy of the photon is much greater than the ionization energy, well, then the electron is going to have even more kinetic energy. So let's work out a binding energy problem. If 480 nanometer light ejects an electron that has 2.16 times 10 to the minus 19th joules of kinetic energy, what was the binding energy? So let's work this out by thinking first about the fact that h nu is equal to hc over lambda, because nu is c over lambda. And so that's the energy of the photon. That's going to be 6.626 times 10 to the negative 34th joule seconds. That's Planck's constant, h, times the speed of light, 2.998 times 10 to the 8th meters per second, divided by lambda. And this is 480 nanometers, so that's 480 times 10 to the negative 9th in meters. This works out to 4.1 times 10 to the negative 19th joules. That's the energy of one photon. So that energy, the energy of the photon, that's going to be equal to the ionization energy plus whatever the kinetic energy is. So that means that the ionization energy is going to be equal to the energy of the photon, h nu, minus the kinetic energy. So the energy of the photon is 4.1 times 10 to the negative 19 joules. And we're subtracting from that the kinetic energy, which was 2.16 times 10 to the negative 19th joules. And that's going to give us 2.0 times 10 to the negative 19th joules. So that's the binding energy, or the ionization energy, of that particular electron. So this is a device called a photoelectron spectroscope. And this is what we use to do photoelectron spectroscopy, which is PES for short, which is nice because it's hard to say spectroscopy. So what they do is they bombard their sample of material with some photons, with energy h nu, and that's going to eject electrons. These electrons are kind of collimated. They go through these sort of lenses that focus the beam, and then they pass through this energy analyzer. So the energy analyzer, I'm not exactly sure how it works, but I think the basic idea is you're causing the electrons to curve because they're charged particles in a magnetic field. Because electrons all weigh the same amount, then how much they curve doesn't depend on their mass, but it depends on their speed. So the ones that have more speed probably get curved less than the ones that have less speed. And then there's an analyzer at the end that will detect the speed of these electrons, which gives you the kinetic energy, and then working out from that what is the binding energy of each of the electrons that's entering this device. So as we read the output of these things, which are called PES graphs, there are a few things to take note of. First of all, the vertical axis is something called the signal intensity. The higher this is, the more like sparks of electrons they got at that energy, and that means how many electrons were at that level that required that binding energy. The horizontal axis is the binding energy. That's the ionization energy. In other words, the amount of energy that was required to remove that electron from the atom. There are some things to note about the scale here because it's a little bit unusual. The first thing is that it's backwards from normal. Most of the time as you go to the right on the horizontal axis, the numbers get bigger. Here as you go to the left, the numbers get bigger. And the second thing is that it's often scaled logarithmically. And the reason for this is because you can have, in one of these analyses, very large differences in the amount of binding energy. And so to put them on a reasonably sized scale, you need to make the scale changing as you go along. So here's what that means. From the first two tick marks, that's 0.1 to 1. The next two tick marks, 1 to 10, then 10 to 100, then 100 to 1,000. So as you're going to the left, not only is the energy getting bigger, but the amount of energy per unit of movement is also getting larger. This is what these things look like. There's spikes you can see. Those represent the intensities. And then the energies are along the horizontal axis. Let's try and figure out how these can be read and made sense of. This is a kind of a cleaned up version of the PES graph for hydrogen, a hydrogen atom. You can see that there is one spike there at one particular ionization energy. Well, there's only one electron, and that electron is coming from the innermost shell, according to the Aufbau principle. Now let's make a comparison. Here's helium next to hydrogen. We see two differences. One is the spike is twice as high. That makes sense because in that same shell, the first shell, the one closest to the nucleus, there are now going to be two electrons because there's two electrons in helium. It also shifts to the left, which means it took a little bit more energy to remove those electrons from the atom. Why would that be? Well, this has to do with Coulomb's law. Thinking back to Coulomb's law, the electrostatic force is equal to a constant number times the charge on one object times the charge on the second object divided by the square of the distance between them. But in this case, that means that constant number times the charge on the nucleus, let's call that Z, times the charge of an electron divided by the distance between them is the radius out to where that shell is, so the average distance from the nucleus. and that's going to get bigger with increasing shells. So for helium, the electrons are still in the same shell, so R really hasn't changed, and the charge on an electron is always the same. But what has changed is the nucleus now has 2 protons in it. So Z is 2 for helium, whereas for hydrogen, Z was just equal to 1. So the amount of force that's pulling on that electron has increased, and so it takes more energy to pull it away from that nucleus, and so that's why that peak has shifted over. Another comparison. Here's helium. Let's put lithium on there. Okay, so lithium has 3 protons in the nucleus, and so that inside shell shifted over, but shell number 1 can only contain 2 electrons, so that means the 3rd electron in lithium has to go in shell 2. Shell 2 is farther from the nucleus. Let's just keep this up here. Remember that the force, electrostatic force, is going to be K times Z times the electron charge divided by the radius squared. So Z is bigger, but also we have this 3rd electron that's in a bigger R. Bigger R means a bigger denominator, and a bigger denominator means a smaller electrostatic force. So it doesn't take as much energy to remove that 3rd electron, and so that's why we get a smaller ionization energy. Another comparison, here's lithium compared with beryllium. Again, we get that shift to the left because Z has now gone up from 3 to 4, and that shell number 2 spike is now 2 times as tall because there's 2 electrons in shell 2 instead of 1. Another comparison, beryllium to boron. So here's where, when they first saw this, they started to see evidence for subshells. Because shell number 2 can contain 6 electrons, but it stops filling that leftmost spike in shell 2 and starts filling another spike with this 3rd shell 2 electron. And again, everything shifts to the left because boron now has 5 protons instead of 4. Z is getting bigger, which means the electrostatic force is getting larger. So this has shown us evidence that there's subshells, that shell 2 doesn't come in just one spike. There's subshells within that shell. Comparison with boron and carbon, shifts to the left. That second subshell in shell 2 starts to increase, goes up to 2. Carbon to nitrogen. Now we see the second subshell in shell 2 go up to 3. Nitrogen to oxygen. Now that second subshell goes up to 4. To fluorine, goes up to 5. To neon, it goes up to 6. And now with these 2 subshells in shell 2, the total number of electrons has reached its maximum. That's 8 electrons in that shell. Neon to sodium. Again, everything shifts over. But now, since shell 2 is full, the 11th electron in sodium has to go to shell 3, and we see another spike starting. Okay, let's step through this and start correlating this to our electron configuration notation. This is hydrogen, and hydrogen is 1s1. This height, the relative intensity, corresponds to 1 electron, and that spike's ionization energy corresponds to the 1s subshell, or the shell number 1, because that's the only subshell. Here's helium. Helium is 1s2. There's still only 1 spike, but now it's twice as tall. Population is twice as high. Lithium. This is our 1s2. This is our 2s1. It's half as tall because there's population only 1 instead of 2. And it's farther from the nucleus because it's shell 2, so that means the ionization energy is lower. We actually jumped over beryllium, but we're seeing the split there. So this is 1s2, 2s2, and that's 2p and it's only one high. That's where boron is. That's its electron configuration notation. Here's carbon. 1s2, 2s2, 2p2. Nitrogen. 1s2, 2s2, 2p3. Oxygen. This is still 1s2. 2s2 is never going to get any taller. It just keeps moving to the left. 2p4. 2p5 for fluorine. 2p6 for neon. Now we filled that shell. Here's sodium. Now we're at 1s2, 2s2, 2p6, and those are never going to get any taller because those shells are full. Now 3s1, and it's way lower in ionization energy. Why? Because it's shell 3, and so the denominator of Coulomb's law is larger, less attraction, easier to remove the electron. Magnesium, 3s1 just becomes 3s2, but everything else kind of stays the same, just shifts to the left because of the increasing nuclear charge. Now we see that split, so 1s2, 2s2, 2p6, 3s2, 3p1 for aluminum. Silicon, 3p goes up to 2. Phosphorus, 3p goes up to 3. Sulfur, 3p goes up to 4. Chlorine, 3p goes up to 5. Argon, 3p goes up to 6, and now the third shell is full. Argon's at the end of the row. So we're starting a row over. That means we're going to see a shift even farther to the left, but now we have to put electrons in a shell that's even farther away. So here's potassium. That's the 1s. This is the 2s, it's full. 2p is full. 3s is full. 3p is now also full. And now we're at 4s, and the population is 1 for potassium. Calcium, everything's the same except for population of the 4s subshell goes up by 1, 4s2. Okay, looking at this, one of the things that you might be asked to do on an exam or something like that is to identify an element from the PES. We can see that it looks like it's a spike too high. There's only one spike on there, so we would have to assume that this is 1s2. 1s2 is helium. Here's another one. Remember, the 1s is always going to be the one that's closest to the nucleus. That's the inner shell, is shell 1. So there's 1s. This is shell 2, 2s, and 2p, and they're full. 2s is 2 high. 2p is 1, 2, 3, 4, 5, 6 high, so that's full. So it's 2s2, 2p6. And then here's 3s. It's full. 3s2 is a full s subshell. And then this would be 3p, and it's 1, 2, 3 elements high. So that's third row, p block, 3 atoms in. So that's phosphorus. Let's try this one on. This is a 1s2, 2s2, 2p6, 3s, population 2, 3p, population 6. So the first 3 shells are full. And then we got these 2 little spikes here. One of them goes up to 2, and the other one only goes up to 1. This one here is the 4s subshell. Its population is 2. What's this one in here? It's a little bit closer. That's the 3D. And its population is 1, because it's only half as tall as, say, the 1s2 and the 2s2 and the 3s2. So this is row 4 and 1 into the 3D block, which makes this element scandium. Notice that the 3D electron is slightly higher binding energy than the 4s electrons. This will have a consequence later on when we start using the structures of electrons in atoms to predict the charges that elements will make when they form ions. Just for fun, I thought I'd throw in a real PES spectra here. Obviously, this is quite a bit messier than the ones that we were looking at, which are kind of sanitized a little bit. But smart people who know what they're doing can make sense of this. And you can definitely see that there are some spikes there. You just need to have a little bit of detailed technical knowledge to know how to interpret them. The consequences of PES findings are, one, that it confirms the quantum nature of electron energy in atoms. these weren't just kind of random graphs with spikes or just curves all over the place, indicating that lots and lots of possible ionization energies existed. There were definite spikes that occur in PES, which indicates that there are only certain amounts of energy that are going to be required to pull electrons out of atoms. And it also shows, as we have seen, that there must be subshells, not just shells.